Alright, here in example 4, the little caption after the word example gives us a clue as to what's going to happen here. Curves that intersect at more than 2 points. So this is a different little twist on this now. We might have, so I'll use black for one curve, like something like this. We might have a point where the blue curve here is under the graph, and then the black graph, and then it goes over. And if we wanted to integrate from, I'll use green lines, from this x value to this x value, let's see here, we're going to have to do 2 separate integrals. Here again, the graphs intersect in the middle and switch. So we're going to have one integral from here to here, where the black curve is the upper curve, and then the blue curve is the lower. So this integral would be black minus blue. And then after this middle intersection point, then they switch places. We're going to have a separate integral. And here we're going to have blue minus black. So we got to figure out where the curves intersect, and then for each interval, which curve is above or below the other one. So this takes a little more work here. But it's going to start out the same. We have the 2 curves. We want to find the area of the region between the graphs. So step 1. Find the points of intersection. We're going to set the graphs equal. F of x is equal to g of x to find intersection points. Find intersection points. So f of x is 3x to the third minus x squared minus 10x. We're going to set that equal to g of x, negative x squared plus 2x. And we should get everything on one side and factor. So I'm going to add an x squared and add an x squared. And I'm going to minus a 2x and minus a 2x. So on the left, we now have 3x to the third. The plus and minus x squareds will cancel. And then we're going to have a minus 12x. And that is now all equal to 0. So from the left here, what can we factor out? Well, we can pull out a 3, and we can pull out an x, and then what are we left with? X squared minus 4, and that's equal to 0. And x squared minus 4, that is a difference of squares, so we can factor that into an x plus 2 and an x minus 2. And then we let each of those 3 factors have a term being equal to 0. So here, 3x equals 0 tells us that x equals 0 is one of our x values of an intersection point. X plus 2 equals 0 means x equals negative 2 is also a point where the graphs intersect. And then x minus 2 equals 0 tells us positive 2 is another point where the graphs intersect. So we're going to start integrating at negative 2, and at 0, we're going to have a point of intersection where the graphs might switch from one being on top to the other being on top. So let's figure out which is above the other. And let me spread this out a little bit here. Okay, our first interval goes from negative 2 to 0. Which graph is going to be higher, f of x or g of x? And I'm just going to rewrite them here so we can evaluate real quick. 3x to the third minus x squared minus 10x. G of x is negative x squared plus 2x. Let's see, right in between these two is the value negative 1. So if I plug negative 1 into both of these functions and see which one is higher, that's the one that's going to be higher for the whole interval. So we're going to look at f of negative 1. So 3 times negative 1 to the third is negative 1, which will make this a negative 3. Minus negative 1 squared is positive 1, so it's minus 1. And then here we have minus 10 times minus 1 is plus 10. So negative 3 minus 1 is negative 4, plus 10 is 6. If we find g of negative 1, that'll be negative 1 squared is positive 1, and this negative makes it a negative 1. Plus 2 times negative 1 is negative 2. And if we find the value of that, we get negative 3. So for this interval, we know that f of x is on top. So for this interval, it's going to be f of x minus g of x. And then, you might want to think, okay, if f of x is higher here, then maybe g of x is going to be higher over the next interval. I'm not even going to compute it. You got to be careful. They could throw a curveball at you, or you might see something like this. And I'll use blue here. Maybe they just touch and it goes right back up. And call the blue function f of x. So for this interval, f of x is above the black line. So here f of x would be our upper function. And then we would have in the next interval, f of x would also still be above the black line. So be careful, be thorough with a problem like this. Don't just jump to an assumption. So now between 0 and 2, we got a nice easy value to look at. That would be positive 1. And let me get this out of here. So we evaluated f of negative 1 and g of negative 1. Now we're going to do the same thing to positive 1, because in this interval is positive 1. So this would become 3 minus 1 minus 10, and that would be negative 12. Negative 12. And if we plug a 1 in here, that'd be a negative 1 minus 2, which would be negative 3. Negative 3 is greater than negative 12, so this interval is going to be g of x minus f of x. So the functions do flip-flop. For a while, f of x is on top, and then for the rest of the interval, g of x is on top. So we are going to have to look at these and evaluate two separate integrals. And we know our upper and lower limits. So let's look at the first one. The first one is from negative 2 to 0. From negative 2 to 0. And here is f of x minus g of x. So f of x is 3x to the third minus x squared minus 10x. And then subtract g of x. Negative x squared plus 2x. And maybe I shouldn't have wrote quite that big, because I got to squeeze in the other interval. So there's the first piece. We've taken care of this chunk from negative 2 to 0. And then we're finding the area between curves. We are going to add to that the next integral. And that's going to go from 0 to 2. From 0 to 2, and now they flip-flop. G of x is first. So g of x is negative x squared plus 2x. And then we're going to minus f of x. 3x to the third minus x squared minus 10x. And I should squeeze in there. We are integrating with respect to x. dx dx. So let's see what we can do to simplify our integrands. So here's from negative 2 to 0. If we distribute this negative, that's going to turn into a plus x squared. And this will turn into a minus 2x. So let's look at our terms. We have a 3x to the third. That stays put. We have a minus x squared and a plus x squared. Those cancel. And then we have a minus 10x and a minus 2x, which turns into a minus 12x. And we are integrating with respect to x. So we need our dx on there. Plus. Our next interval goes from 0 to positive 2. And let's see here, when we distribute this, is going to become a minus 3x squared. This will turn into a plus x squared and a plus 10x. So again, we have a, that should be third power. A minus x squared and a plus x squared, those are going to cancel. We do have, though, a minus 3x to the third. And then we have a 2x plus a 10x. That becomes a plus 12x. We are integrating with respect to x, dx. So I can probably get rid of this. And now we take the antiderivatives. So this, we move the power up by 1. That becomes 3x to the fourth. And we're dividing by 4. 3/4 x to the fourth. minus, this will become 12x squared divided by 2, or 6x squared. And we're evaluating this definite integral from negative 2 to 0, plus. Here, again, we raise our power by 1. That becomes x to the 4th divided by 4. And then the 12x squared, or 12x, becomes 12x squared divided by 2, or 6x squared. And we are evaluating this integral from 0 to 2. All right. So we just got to start working our upper and lower limits in there and find this value. And good, each of these integrals does have a 0 somewhere in it. In one it's the lower limit, the other it's the upper. So here we plug in the upper limit, zeros, and since each term has an x, those just go to 0. 0 minus. And then we're going to plug in our lower limit, negative 2. So let's see here. What do we have? Negative 2 to the 4th power. Since it's an even exponent, it's going to become a positive value, and 2 to the 4th, 2 times 2 is 4, times 2 is 8, times 2 is 16. That becomes 3/4 times 16. And then we are minusing, minus, plug that negative 2 in here. Negative 2 squared is 4, positive 4, times 6 is 24. And then we're going to have plus, and let's see here, we plug in our upper limit, and that's going to become negative 3/4 times 16, plus, plug the 2 in here, 2 squared is 4, times 6 is 24, and then we minus, plug in our lower limit of 0, each term does have an x, so those both goes to 0, and it would sort of be a minus 0 in there. So let's see what we got. 3 times 16 is 48. 48 divided by 4 is 12, and we distribute this negative. That's going to be a negative 12. Distribute the negative again. That becomes a plus 24. Plus. And here we have the same scenario as in the first term. 3 times 16 is 48, divided by 4 is 12, but this is a negative 12. So this will be a minus 12. And then we have our plus 24. And let's see what happens. We have a negative 12, and another negative 12 is negative 24, which will take out this positive 24. Those all equal out to 0. So we're left with 24. That is our final answer. The area between these two curves where they intersect is 24 square units. And that's a nice even number for something that is not a nice geometric shape like a square or a triangle. So let's see here what this looks like. Here are our curves. Our first interval went from negative 2 to the origin, and on that part we had our upper function was the third power function, 3x cubed minus x squared minus 10. So we found the area in between the curves here. But then at the origin they switched, and the negative x squared plus 2x curve now became the upper function, and we subtracted the cubic function and found this region. And when we add those regions together, we did get 24 square units. Note, in this example, you obtain an incorrect result if you integrate from negative 2 to 2. You know, if we had tried to do that example, f of x minus g of x from negative 2 to positive 2, we would have got an answer of 0. If the graph of a function of y is a boundary of a region, it's often convenient to use representative rectangles that are horizontal and find the area by integrating with respect to the y-axis. In general, to determine the area between two curves, we can use the area is equal from x1 to x2, the top curve minus the bottom curve, for vertical rectangles or variables of x. But other times it might be better to use horizontal rectangles to integrate from the y-axis, from y1 to y2, the curve on the right minus the curve on the left, integrating with respect to y. where x1, y1 and x2, y2 are either adjacent points of intersection of the two curves involved or points on the specified boundary lines. So let's check one of these examples out. So we have here horizontal representative rectangles. Find the area of the region bounded by the graphs of x equals 3 minus y squared and x equals y plus 1. So our first order of business is to find the intersection points, and we set them equal. 3 minus y squared is equal to y plus 1. And let's get everything, well, since this y squared is negative over here, let's move everything to the other side. Negative y squared jumps over and becomes positive y squared. We already have a plus y over there, and then we subtract 3 from both sides to get a minus 2. And this is all equal to 0. So we factor. And the factors of y squared are y and y. Factors of 2 are 2 and 1. We want our middle term to be positive, so we want a plus 2 and a minus 1. Set each factor equal to 0, and we get y equals negative 2 and y equals positive 1. So I'm going to write those up here in the corner. Y equals negative 2 and y equals positive 1. Now we got to figure out which curve is greater than the other, or to the left or to the right. And it's nice because right in between negative 2 and 1, we have a value of 0. So let's plug 0 into each function. So here, if we plug a 0 in for this y squared, we get x equals 3. And if we plug a 0 in for y here, we get x equals 1. So from the perspective of the y-axis, which of these is closer to the y-axis? Well, it looks like it's going to be this one. This gave us our lower output value, so this function is on the left. And let me even write that on there. This function will be to the left, and our squared function, x equals 3 minus y squared, this will be the one on the right. And if we pop back here for a minute, we've got to remember if we're on the x-axis, it's top minus bottom. If we're on the y-axis, it's right curve minus left curve. So let's set up our integral. We're going to have a definite integral from the y values we found here, from negative 2 to 1. And then we want to do right curve minus left curve. So our right curve is 3 minus y squared. Minus our left curve, y plus 1. And we are integrating with respect to y. So let's distribute the negative and collect up any like terms. From negative 2 to 1. Let's see here. I'm going to start with my squared term first, so this is going to be negative y squared. Distribute this negative, and that will become a minus y. And distribute here also, and this becomes a minus 1. And we have 3 minus 1 is 2 plus 2. And we're going to integrate that with respect to y. So let's integrate. Negative y to the second power is going to become negative y to the 1 power higher divided by that new power. Minus y to the first becomes y squared over 2. Oops, I don't like the look of that squared. Y squared over 2. Plus this becomes 2y. 2y. And we are integrating from negative 2 to 1. And I could probably get rid of this up here. Again, neither of our upper or lower limits is 0, so we are going to actually do a little work here. This 1 is nice, though. When we plug that 1 in for any y, we're going to get negative 1 to the third is 1 over 3. Minus 1 squared is 1 over 2, 1/2. Plus 2 times 1 is 2. There's our upper limit evaluated. And then we are going to subtract from that our lower limit evaluated. So plug the negative 2 in. So negative 2 to the third is negative 8, and it hits this negative and becomes a positive 8/3. We plug the negative 2 in for this y. Negative 2 squared is 4. 4 over 2 is 2, minus 2. And then the 2 pops in here, the minus 2. 2 times negative 2 is minus 4. And if you get common denominators, collect up all your like terms, you're going to get 9 halves. 9 halves square units. And let's see what this one looks like. So first we set our functions equal, and we found the y values where the functions intersected. Here at a y value of 1, and then here at a y value of negative 2. And then we wanted to figure out what curve was to the left or right of each other. So we took a number in between 1 and negative 2, and 0 fit the bill just perfect. I plugged 0 into each function and found 2 values, 1 or 3. The 1 was the lesser of the 2, so that was to the left. So we knew the function to the right was our curve, our squared term, 3 minus y squared. So this was our curve on the right, and we had our curve on the left. That was how we subtracted them. The curve on the right, this one, minus the curve on the left, gave us our representative rectangles in between those two functions. So in example 5, notice that by integrating with respect to y, you need only one integral. If you had integrated with respect to x, we would have needed 2 integrals because of the upper boundary would have changed at x equals 2. So we could have done this problem from the x-axis, but it would have been a little more complicated. You know, we would see here from x is negative 1 to here, where x is equal to 2, we would have integrated with the straight line on top and subtracted the parabolic curve. But for the rest of the integral, we would have had the parabolic curve as the upper limit and as the lower limit. So we would have had to break that into 2 separate functions. The upper half would be y equals positive root of 3 minus x. And then the lower portion of that would have been y equals negative the root of 3 minus x. And this would have made, as you can see, a much more complicated process to get that same 9 halves. Now let's talk about integration as an accumulation process. And we did talk about this when we first started finding the area under a curve. In this section, the integration formula for the area between curves was developed by using a rectangle as the representative element. For each new application in the remaining sections of this chapter, an appropriate representative element will be constructed using pre-calc formulas that you already know. Each integration formula will then be obtained by summing or accumulating these representative elements. So we're going to take a known pre-calc formula, use that to figure out our representative element, and use that to find our new integration formula. For example, the area formula in this section was developed as follows. Area equals height times width, or delta A. A representative rectangle is f of x minus g of x times delta x, the width of that rectangle. And then we turn that into an integration from a to b, f of x minus g of x dx. And in this example, there's nothing really to write down, but it says here, find the area of the region bounded by the graphs of y equals 4 minus x squared. That's a downward opening parabola, y-intercept of 4, and the x-axis. Describe the integration as an accumulation process. So the area of the region given by, here's our integral from negative 2 to 2 of 4 minus x squared dx. We can think of the integration as an accumulation of the area of the rectangles formed as the representative rectangle slides from our left value of negative 2 to the right value of positive 2, as shown in the figure. So let's check this out. Here's our parabolic curve, and we start integrating at the left endpoint negative 2. The integral from negative 2 to negative 2 of any function, if our upper and lower limits are the same, the area is 0. But let's start to slide out along the x-axis. What happens when we integrate from negative 2 to negative 1? Now we actually have a little area under there. So that becomes 4 minus x squared dx. We integrate, evaluate our upper and lower limits, and we get this area is 5/3 square units. But let's slide our point more to the right. Let's accumulate some more area under the curve. So now we slide out to the y-axis, or an x value of 0. So now we're evaluating our integral from -2 to 0 of the same function, dx. No surprise, we now have more area under the curve. 16/3 square units. Let's continue to accumulate more area. So now we're going to slide out here to a x value of +1. So we're integrating from -2 to +1 of the same function. We integrate and evaluate and get 9 square units. So we went from 5/3 to 16/3. This in thirds would be 27/3. So we are accumulating more area under that curve. And let's polish it off. From -2 to +2. Now we're looking at the entire area under that curve. We integrate and get the area as 32/3 square units. So think about, we're sort of rolling out. We're sliding our left endpoint toward the right endpoint. We're accumulating more and more area underneath that parabola.